So let's say x is exponential random variable with parameter lambda, and so then we know that it's given by the density function that we defined above. Right? So then what I can do is, let me erase this. So then I take x to be this. So now an interesting property is the following. Suppose I look at the chance that x is bigger than s plus t. Okay? So this I know, let's say for s and t non-negative. This I know from the above calculation is e to the minus lambda times s plus t. So now I do the same thing. So I look at the chance of x is bigger than s plus t, given that x is bigger than t. So what is this? Before I do the calculation, so what is intuitively, what does this mean? This means I want the conditional probability of x is not decayed till x not decayed till s plus t, given x has not decayed till t. Okay, so that's the key. That's what I should understand. Right? So I want to understand x is not decayed till s plus t, given that x is not decayed till time. Okay? So that means if you look at the number line, look at the simple number line. So you look at this line like this. So I have the time point t here, and I know I have not decayed till now. Until now I have not decayed. So x is not decayed. And then what I do is, post this, I want to know what's the chance that I have not decayed. Given this event in red, what's the chance that I don't decay at time further. So if you want to compute this probability, so let's go back here, let's go down here. So what is this going to be equal to? This is going to be equal to the chance that x is bigger than s plus t, right? And x is bigger than t, divided by the probability x is bigger than t. And that's going to be equal to 1. So the top guy, I have s plus t and x bigger than t. But x bigger than t is contained in x bigger than s plus t. So the top is just going to be the chance that x is bigger than s plus t. The whole thing divided by the chance that x is bigger than t. And that's going to be equal to what now? The top is e to the minus lambda s plus t, right? And the bottom is e to the minus lambda t. So let me just write this in red. So let me go back and write this in red. So t is in red. Understand this. So the idea was that x is bigger than s plus t, given x is bigger than t. This is what we had. And here we have this. So now that means this, and this. The t goes away, and all I'm left up with is e to the minus lambda. But that, if you stare a little bit, what is that? That's the same as x is bigger than s. So what have we shown? Yes. So what have we shown? We've shown that the chance of x bigger than s plus t, conditioned on the fact that x is bigger than t, is the same as the chance of x bigger than s. Right. So this is called the memoryless property of exponential. So let's go back and erase it. So x is kind of memoryless. If I know I have not decayed till time t, the chance that I have not decayed for the time s is just the same as restarting again. So this is called the memoryless property of exponential. So now here's a simple exercise for you to think about. So I've given you an example of a continuous one that does this. So is there a discrete random variable x that has the same property? Is there x discrete with memoryless property? And is there a connection with is there a connection of that with exponential? So I'll like think a little bit. Maybe you can. I'll give it the homework this time, perhaps. So the next example is very fundamental. It's called the normal random variable. So it's called the normal random variable. It's probably used the. It's probably the. It's the most widely applicable random variable in, in all of statistics and probability. Sorry, it's called the. It's also called sometimes as the Gaussian random variable. Or Gaussian distribution, or in various ways. It's a fundamental object. So how did it come? Let me just discuss how it comes about. Then we'll sort of motivate it in that fashion. Of course, the motivation run, the importance runs far beyond the motivation that I'll present. So let's recall a little bit. Let's go back, recall a little bit. This is way back in the first 2 weeks we did this idea that let's say xi's were coin tosses. So xi's were distributed as Bernoulli p. That is, so I think I use the notation xi is like this, Bernoulli p. That means xi's are 0, 1, and the chance that xi is equal to 1 is equal to p. Right? So this sort of gave you, and I took independent. Let's say independent. So IID. So I is equal to 1 and independent. Then from this, we also know from long time back that if Sn was the sum from I equal to 1 to n of xi, then Sn was a binomial. So now, given this, I showed you this following idea last time, long time back, that I said if I took p to be very, very small compared to n, if p was depending on n, and sorry, what's going on? P sub n was like lambda sub n, lambda by n, and I took Sn, and I looked at the chance that what's going on? The probability Sn is equal to k for a fixed k. This, as n goes to infinity, converges to e to the minus lambda power k by k factor, right? For all k. So all this we have seen earlier, and this we called as the Poisson lambda distribution. So now, if p gets smaller and smaller as n gets larger and larger, and p by n times p was a constant, then this is what we would get. So this p was like lambda. So now what happens if P stays fixed? So let's say P is a fixed number. So what happens? So here's a question. What happens when P stays fixed? So 0 less than P less than half is a fixed number. Is it fixed? Is it fixed? What happens to Sn as n goes to infinity? So if P stays fixed, what is the behavior of Sn? If P stays fixed, let me just take this thing down. What is the behavior of Sn as n goes to infinity? So here, the idea is that okay, if I do probability Sn equal to k, then I may not get the right answer. So it's not nowadays viable. So it's like sort of a very it'll just decay to I mean, yeah, you'd appropriately scale it to see what it converges to. But let's just do how the distribution function looks like. So now I want to understand the chance that, let's say, A is less than or equal to Sn is less than B. What are these? As n goes to infinity. So I don't know if you've seen this. If you think a little bit. So if A and B don't change with n, okay, then one can understand this. What is Sn going to be? Sn is the number of successes in n tosses, right? That's the definition of Sn. Right? That's binomial. That's what Sn is. So now, if A and B don't change with n, then this probability is kind of going to go to 0 because your Sn is going to be larger and larger with significantly higher probability, and A and B will be left out of the. So this is something that you have to think a little bit. I'll let you think a little bit. So in some sense that the mean of Sn, we have seen this before in calculation, the mean of Sn is n times P, right? So as n gets larger and larger, and you know that the variance of Sn is n times P times 1 minus P, right? So in some sense, as n gets larger and larger, n gets large, A and B will not belong to the quote unquote the range of Sn. That is which we thought of as that is the mean of Sn, right, minus the variance n times P1 minus P on standard deviation, sorry, plus this and square root of n times P1 minus P plus n. Will not belong to this. So is this formal idea clear? That so this was we discussed the range of Sn as the standard deviation of Sn, and this was the mean, right? The mean of Sn. So and same thing here, right? This is also. So we will erase this. So these two were the standard deviation of Sn, and this was the mean of Sn. So in some sense, we discussed a long time back that the mean plus the standard deviation and mean minus standard deviation is going to be the kind of the quote unquote range of random variable. So in some sense, you would expect A and B. Okay, this is clear that A and B will not be in this range after some time because as they get larger and larger, NP is going to infinity, and the square root is a little smaller. So you will eventually avoid A and B. So with high probability, A and B will not be in this. So this probability that we have there is going to go to 0. So you will have to scale. So a more meaningful understanding is. So a more meaningful question is. You have to scale with this idea. So the more meaningful question is to understand the following. So take an A and a B in R, right? A less than B, let's say. A more meaningful question is what happens. So this is a more meaningful question. What happens to the chance that A, so you keep adding, you look around the mean. You look around the mean is less than equal to Sn, is less than equal to B, sorry, BA minus NP, or A plus NP. So look around the mean and B plus NP around the mean, and you scale by the variance. You scale by the interval. That is the square root of n times p times 1. You look around this interval. So this interval keeps moving around with what happens to this. This is a more meaningful question. So in some sense, this is where the random variable is going to be supported on, and you want to understand what's happened to this. So as n gets larger and larger, this is where the random variable is going to be. So this is not, I made a mistake. So let me erase it. So let me come back. Let me go to here. Let me copy it. So more meaningful question is, so A and B is not in this, is going to be 0. So more meaningful question would be how to find, look at how Sn is in the interval around NP. Right? So you look at NP, and then you look at, let's say, some A times square root of n times, sorry, A times, yeah, n times P times 1 minus P, right? And B, so let's say NP times plus B times square root of NP. So how does Sn behave? How does the probability of this? What happens to this as n goes to? Right? So here A and B are fixed. A less. So you look around NP, you scale to the width of the standard deviation, and you look at how this interval behaves, because that's how your range is going to behave in some sense. So in some sense, you'll have to identify. So the question is, so what you identify is you identify the chance that A is, I'll rewrite this probability, A is less than equal to Sn minus Np divided by square root of Np times 1 minus P is less than equal to. What happens to this as n goes to P? That's a more meaningful question to answer. So what is this? So let's see. Let me now motivate a little bit. So what is going to be? So this, if you look at it, you look at this. It's just going to be like. So you look at, to understand this question. So you look at A sub, let's say A sub k, A sub n, which is set of all k, such that np plus A times square root of np and 1 minus p is less than equal to k, is less than np plus B times square root of np times n. Right? Take this event k, this event as k, and the above probability is what? The above probability, so let's call this a star, or let me just make this, let me copy this. So this guy right here, let me duplicate it. This guy here is going to be again just the same as the sum over k in an, right? Probability of Sn equal to k by definition. That's what it's going to be, right? Now what's that going to be? That's the sum over k in an. This is going to be just n choose k. So n choose k, right? N choose k. P power k, 1 minus p to the power n minus k. That's what it's going to be like. That's exactly what it's going to be like. That's the formula, right? Now is where the key is. So this is where the jump is. So I'll write the jump in the proper way. So you use Stirling's formula. Stirling's formula. And you have to use the definition of Riemann integration. So because I've scaled everything correctly by this fashion, my AN is defined in these small sets. What will happen is that this will converge, because it's a big leap of faith. As n goes to infinity, if I do this factorials properly, it will converge to a to b e to the minus x squared by 2 over square root 2. This is something that one will have to show. So of course, to do this jugglery requires some work. This is non-trivial. This is non-trivial. To do this. So that's what's happening to this probability. So this is a fact that one can establish. So this is what gives rise to what's called the Gaussian density. So this is what's called the Gaussian density. And this is something that we will do maybe in about 4 weeks from now, the last week of class. That this phenomenon, this is something we'll revisit. This phenomenon is universal. The central limit theorem will tell you that this phenomenon is universal. This above phenomenon is universal. So in what sense, I'll explain later on in class. I'll explain last week. In last week of class we will do. But as of now, the idea is that let me go back to split view. You see the split view works correctly for you. Very good. Again, right. So this is the motivation for what this density function that I'll define in a second. I have not defined it. I've just shown you a limiting idea. So here's the idea, right? So you take a binomial variable. You know that if p by n times p is a constant, then it goes to a Poisson. But if p was fixed, you notice first thing you notice that the mean of Sn is like n times p, is growing. So is the variance. Okay, it's n times 1 minus p. So your random variable, in some sense, it's going to be around np plus square root of np times 1 minus p and np minus square root of p. So then you can try to understand how this random variable is behaving around that value. That's what I'm doing next. I'm taking probably Sn equal to this, belongs to this. I want to know what happens to this as n goes to infinity. So then I do this calculation. I write the event down properly. Then this is just a sort of a detailed maths exercise. One can sort of do this properly. That if you use Turing's formula and for the factorials and Riemann integration ideas properly, you can actually show that this combinatorial sum converges to the integral. And what so happens is that that function there is it's called the Gaussian density, and it's sort of universal. It happens for random variables that are not just binomial, but looks like sums of IID. That we will come to in the last week of the class. Now let me just do this. Let me go back and let me define the normal random variable for you. So here's the definition of our normal random variable. So here's the definition. So X is said to be normal with mean mu and variance sigma square. I'll explain to you why this mu and sigma square come and why it's the mu and why it's sigma square. Because this parameters mu and sigma square will come to maybe in a couple of weeks time. Mu is a number in R. Sigma is a typically a positive number. If x has probability density function given by f sub x is equal to 1 over sigma times square root 2 pi e to the minus x minus mu whole squared by 2 sigma for x. So we will later show the importance of mu and sigma squared. In the above example, in the above calculation, mu was 0 and sigma was 1. So that is x was normal 0 1 in this calculation. In the above calculation. Yeah. So this is what we will try and see. Of course, now this implies what? This implies the chance that x is in, let's say, a less than x less than b, or less than b, is the same as the integral from a to b e to the minus y squared by 2 by root 2 pi dy. And here, of course, now if you stare at this little bit, this integral has to be evaluated numerically. So there's no antiderivative. So this is something that one has to learn how to do these probabilities. So I'll discuss this in an exercise or in next class, depending on how I want to proceed. But that's the formula. This comes out to this is called the normal dynamic. It's kind of a very fundamental objective problem. And I gave you one motivation of it using the central limit theorem, but using the binomial random variable, which is part of this universal class of results called central limit theorem.